Thank you for your kind presentation and for the invitation to deliver this plenary lecture. So, artificial intelligence has become a part of our everyday lives, as we all know, and changed the way we work, we communicate, and make decisions. And as a result, the application of AI in the field of structural integrity has a significantly grown and is expected to play a key role in the future research and engineering practice. Here I reported a graph taken by Scopus with a search with terms artificial intelligence and structural integrity. You can see a dramatic increment of the number of papers in the last few years. What about additive manufacturing? The trend is the same. You can see that we have an increase, and this trend underscores the key role of AI in the AM research and its growing importance. But what do we mean with artificial intelligence? We talk about this. For example, here I reported two definitions by a report of the European Commission. So if I read the first one, AI refers to systems that display intelligent behavior by analyzing their environment and taking action with some degree of autonomy and to achieve specific goals. Okay, but from our point of view, what does it mean? In more engineering perspective, what is? But very briefly, this is the scheme of a traditional programming sequence. So the programmer writes the series of instructions, the behavior is rigid, it follows exactly the rule written by the programmer. For example, we have a series of instructions to compute the energy absorbed, starting from the experimental data, for example, for the first-time cars. And we have a very rigid structure. For artificial intelligence, we need data. So the system does not rely on predefined rules, but learns from data to build its own model. They discover pattern relationship from the data rather than following rigid instruction. And this is very important. It performs well in complex and nonlinear scenarios. For example, we provide several first-time cars and the computer absorb energy, and the AI algorithm will learn how to compute the absorbed energy directly from this experimental data, for example, impact test. So this is a quite different approach that we can follow. And indeed, we are moving from empirical knowledge, from observation and experience, to the AI-based knowledge, in which learning and adaptation is fundamental. And for this, we need data, we need very good data, and we must rely on the data that we have. So, but after this brief introduction, what about AI and this aspect, the aspect that we have highlighted in AM? How can we exploit in AM? I have found four different trends. For example, AI for process monitoring, in which AI-based detection of defects and anomalies and adaptive control process parameters. We have seen an example in the previous plenary. AI for design optimization. So we can link to topology optimization or to the generative design to see which is the best production process. And then we have structural integrity assessment, so data-driven prediction of material properties and prediction defect, residual stress, failure modes, and something which is related to structural integrity. Then we can have AI for material discovery and metamaterial structure. We can discover new material, or we have an AI enabled for the design of metamaterial with tailored properties. This is not strictly related to additive manufacturing, since we can design any kind of metamaterials, but additive manufacturing allow to design, to produce these metamaterials. So this is why they are linked. In this presentation, we focus on this topic, okay, since it is the one I have worked on. And so the objective of this presentation is to show research activities carried out within the research group, okay, I belong to, and they focus on prediction, the fatigue response of AM parts starting from the process parameter, and this has been integrated also in a topology optimization framework, and the prediction of the response of lattice structure produced by AM. We have also other research, but there is no time to present all of them. And the second one, very briefly, to discuss the potentiality, the current, and the future research trends of AI applied to the structural integrity of AM parts. So let's focus on the first one, the first activity. But why do we need? Which is the problem that we would like to solve? The fatigue response of AM parts is worse than that of traditionally built parts, and this is mainly due to manufacturing defects. which randomly formed during the AM process. We all know here, since we talked about structural integrity. And this defect induces a large experimental variability. You can see some of experimental data taken from the literature for the titanium alloy, and you can see that there is a large scatter. This complicates the prediction of the fatigue response and subsequent design against fatigue failures. But which is the responsible for this variability? For example, process parameter and post-treatment affect the microstructure and the defect population, and so they affect the fatigue response. So the process parameter should be considered as an input for the prediction of the fatigue response. This could make the process more efficient, okay? But we have a large number of process parameters, and we cannot find, for example, a design of experiment to find the relationship between the process parameter and the fatigue response. It's very complex, it's not feasible, and we don't have that money to do it. So the objective of this first activity is to develop a methodology which allows to safely design AM parts with the topology optimization algorithms, but this in the last framework that I will present. But the first thing is that we want to start from the process parameter by exploiting the potentiality of machine learning algorithms. So here I report the process parameter. We rely on literature data, so we consider this one, the most important one, and the range are those available in the literature. We consider also the heating temperature to take into account the heat treatment and also surface finishing processes, this one. And we consider them as Boolean features. So if the process is present, we set the Boolean feature to true, otherwise we set to false. Okay. The post-treatment input can be varied depending on the material considered for the validation, since we have validated the different algorithm, different material, and we have to trust on the data that we have found in the literature and that are available in the literature. Okay. So we mainly use neural network. This is a very brief introduction to neural network. They are operators that replicates in a general view the brain structure. They have a layer structure. Each layer is composed of different neurons fully connected between them. Then we have to tune these parameters in order to replicate the relation between the inputs and the outputs. Okay. This is a very straightforward approach. This is a black box approach. Okay. But it has a main drawback. It is purely data-driven, so it requires a large data set, and the prediction will be physically inconsistent. Why? Because we must consider the data. They have a large scatter in the literature, and so we can obtain that some predictions that are not consistent. So this is a quite typical scheme. We have an input, the process parameter, and output the fatigue response. If we have an input, the applied stress amplitude, we can compute the fatigue life, and then we can obtain the PSN curves as an output. But as I told you, the black box approach has some drawbacks, so we embedded physical knowledge to make more real and more accurate the prediction. And this, I show how we embedded this physical knowledge. Okay, this is the widely known Murakami formulation. If we talk about additive, everyone knows it. Okay, and this formulation can be rearranged and can be shown that the fatigue response is proportional to the microstructure, the Vickers hardness, and is inversely proportional to the defect size. Okay. And these information are elegantly condensated in this very beautiful formula. So we use this as a reference. This is the scheme that we use. The input are the process parameter, and we have a first neural network which predict, which start from the process parameter, the treatment characteristic to predict the influence of the microstructure. Then we have the second one, which predict the influence of defects. In this case, we don't consider the treatment, since the defects are not so much influenced by treatments. And the last one concatenates these two inputs, and with the number of cycles can predict the fatigue life. Okay, you can see the fatigue response. So the neural network and the physics for neural network, this one has been validated in literature dataset obtained by testing the aluminum silicon 10 magnesium alloy. Okay, we take this data from the literature and we consider a powder laser beam process. Okay, And you can see this one is the loss function for the mean square error, the black one for the black box approach, and this one, it is the one for the physics-informed neural network. We obtain a better accuracy by embedding physical knowledge. And you can see this is a result of the validation we have made, but I reported on this. And this has been obtained by considering the physics-informed neural network. Here you can see the physics-informed neural network. This red curve performs quite well also in the very high cycle fatigue life range, which is for which we have no data. In this case, on the other end, we have not very good prediction without embedding physical knowledge. So this underscores this importance. And this is only visible here. Here we have a two stress amplitude, 80 megapascal and 100 megapascal, and we predict the influence of the H distance. It is a widely known parameters. If we increase the H distance, the fatigue response decreases. Okay. For the feed forward, the black box approach, we have not we are far from the experimental data, and the trend is not respected. With the physics-informed neural network, we can capture this trend, and the data are very close to the experimental one, which are those in red. Okay, so we are able to predict a trend which is widely known in the literature. So to conclude this first activity, this work has demonstrated the proposed physics-informed neural network can reliably predict the fatigue response starting from the process parameter. It is possible to leverage literature data, otherwise they are waste. So if we can improve the prediction and add more data, we can limit the time necessary for experimental tests, which are very time consuming. And it is fundamental to include physical knowledge. We started from the Murakami formulation, but these other physical knowledge can be embedded to improve further the prediction. Okay? But we are talking about fatigue, which is the main drawback of this. The models are deterministic, okay, and cannot capture the experimental scatter. But the fatigue life or additive manufacturing parts show large variability, and this must be taken into account. We cannot design by taking into account a deterministic value, okay, or a median value. So we have developed a new algorithm, and for each data set, the R90C90 curves has been estimated. This curve is commonly used in industrial practice for the design of against fatigue failures. It represents the lower bound at a 90% confidence level of the PSN curves with a 90% reliability. Okay, these curves take into account two types of scatter: the scatter associated with the fatigue phenomenon, with the reliability level, and the variability associated with the estimation process, with the confidence level. We estimate this one by shifting this curve, the median curve, by a factor according to the modified OM method, which is widely known in the literature, and we can take this very conservative curve used for the design. It is important to remark that this curve takes into account experimental variability and estimation uncertainty. We add another type of variability. So this is the neural network. We have the process parameter and the stress amplitude, and then we add the R90C90. We have in output the R90C90 number of cycles to failure, but we exploit the characteristic of the Bayesian neural network. We obtain non-deterministic prediction. So we repeat the prediction many times, and we obtain a green band which represents the uncertainty and the prediction. So to conclude with this approach, we can separate the experimental uncertainty with the uncertainty in the prediction. Okay. The R90C90 curve, which have been considered in the training dataset, model the variability intrinsic to the fatigue phenomenon and the uncertainty in the estimation process, since we can have a dataset with less data. The iterative prediction with the neural network model the uncertainty associated with the neural network prediction. Okay, so this is very good for fatigue, and since we start from literature data, which may have and we can have variability in the prediction. Here you can see the results. This bundle of cards include experimental data. We have also other validation, but I have focused on this one. And you can see that where we have less data, where we have more data, we have a smaller range of the prediction. Where we have less data or run out, we have a larger range of the prediction. And this is quite expected, and this is good from our point of view, since where we have less data, we are less sure to estimate the curve, the real curve. Okay, now that we can predict the number of cycles to failure, okay, how can we integrate this into a design process? We have developed a framework. We have include all this information into a framework which exploit with topology optimization, in which we can start from the process parameter. So the input are the process parameter. The machine learning output provides the R90, C90 stress amplitude at a defined number of cycles. We have to decide which one. And this is the input for the topology optimization process. In this process, we keep the first principal stress, which is responsible for crack propagation, below this limit value that we have estimated with machine learning. So we have a process which takes into account during the topology optimization the effect of the process parameter and their influence, and this is not done in the literature and the industrial practice. In general, only static properties are considered. So we have validated this one with this CAD bracket that you find in the literature with this material, titanium. This is the training data set taken from the literature for the titanium alloy. Here you can see where we have selected the number of cycles to failure, okay? And here is the results. This is the components which is optimized against fatigue loads, and we're starting from the process parameter. So the first principal stress is kept below the limit stress. We have obtained a final mass which is well below with respect to the initial mass, and this is very good. But the most important thing that if we want to produce these components and we have a set of process parameters, we can take into account directly before the optimization process, which is the limitation. We have not yet validated it experimentally, okay? But it has the potential for making the design against fatigue failure of additive manufacturing parts very efficient, which is something quite new and not considered in the literature. Okay, so another point. During this activity, we have collected the literature data, many, you can see here, and we ask ourselves, can the information obtained from one data set be leveraged also for other materials, okay, especially if we don't have another data? The answer is yes. We can use transfer learning algorithms. Okay, all the data reported here for free material. And let's suppose that we have a lot of data for the aluminum in 316 steel and less data for the titanium alloy. Okay. The neural network has been trained by considering all data for the titanium and steel alloy, as in the previous case. This is quite common. But the data for the after that we consider data for the aluminum alloy, but only the last layers are trainable, okay, and are trained with the aluminum alloy. And in this way, the latent relationship learned from the previous alloy is preserved, and the last layer, which is free, can adapt to the new training data for which we have less data, okay? So we can try to exploit the relationship learned from other data sets for which we have more data. Here you can see the normalized R-squared value with respect to the one experimental for a specific data set. Here we have the number of titanium data from 50 to 200. And here we have the normalized R-squared value computed by considering only the titanium data, so from 50 to 200 data. And here we have the normalized curve computed by applying transfer learning, so pre-training with aluminum and steel, and increasing the number of titanium alloy. You can see that we have a significantly faster convergence of the machine learning algorithm based on transfer learning approach. So if we use transfer learning, we can obtain, even with limited data, a good prediction, okay? And here you can see the same things. Here you can see that for 50 data, the estimated curve with only the data for the titanium alloy are not good. On the other hand, the data for the curves for the after transfer learning are quite good, and with 100 data, the situation is better, and we have a very good prediction. Okay, so in this case, we have exploited the relationship properly. And to conclude this activity, transfer learning provides very good prediction even with only 50 data. So I have shown some nice application of the fatigue regarding the application of artificial intelligence for the fatigue response. And you can see that it can support properly the design. And if we have a good data, but we can exploit also relationships that can be captured from data different from the target one. Here I will go to the last activity I would like to present because it is another application of artificial intelligence in a different way, okay? And they focus on lattice structure. They are commonly associated to additive because they can be produced only with AM process, and they are difficult to be designed with other to be produced with other manufacturing process. But they have some drawbacks. They are very small, and the simulation can be computationally expensive. And we have significantly difference between the original CAD file and the manufactured geometry. So this strongly affects the mechanical response. We'll focus on this octet truss, lattice structure. And here you can see the two main defects, who are internal porosity defects. Here you can see someone taken at the JTech Center in Politecnico. And here you can see the surface roughness of the beam and the which have an influence of the compressive response if we want to absorb energy. We develop a multi-scale approach. Our objective is to define a simplified methodology. Okay, so this small portion of the beam contains a defect and a surface roughness. So we would like to model the effect of defect and surface roughness of the stress on the stress strain curves. And then we put these stress strain curves into a specimen, which I've also tested experimentally, to verify the influence of these two deviations from the original CAD file. Okay, so this is the finite element model of the specimen. Here you can see the RVE with the defects. We take into account also the orientation of the defect. Okay. And here you can see the different stress strain curves due to the presence of the defect and a specific roughness. Then each element of this curve has been randomly as a random stress strain curves, which derives from a specific roughness and a defect. Okay, and we made a simulation with 1D elements, and the procedure has been repeated, varying the position of these elements in order to take into account the random location of defects. We don't know where defects can be at the beginning. So this is the comparison with the experimental data, and you can see that we obtain a good prediction, okay? And we have a range of a scatter of the curve due to the presence of defects. But why do we need the machine learning? This activity seems to be completed, okay? The statistical multi-scale approach requires multiple finite element analysis of the beam, and the variation of the defect characteristic and of the roughness requires a new set of computationally expensive simulation. Okay, so machine learning can be used as a surrogate model to estimate the stress strain curves from defect characteristics. Okay, for example, we can have an input the defect characteristic, the maximum diameter, the aspect ratio, the orientation, the location, and the surface roughness, and we have in output the characteristic of the stress strain curves, so the yield stress, the yield strain, the tensile stress, and the strain at failure, for example. Okay, here are some parameters for the validation, but they are not important. And here you can see the red curves are those obtained with the simulation, and the blue one are those obtained with machine learning. So we have a good prediction, very good accuracy, but the machine learning time for each defect configuration is less than 1 second for each defect configuration. If we simulate it, it takes a longer time, okay? So let's try to conclude a bit this presentation. The main question is, during the conclusion, is artificial intelligence truly useful supporting the design or structural integrity of additive manufacturing parts? Or is it just a trend or a moda, as we say in Italy? Okay. Machine learning, artificial intelligence can manage multivariate and complex problems, and it can do very effectively. Okay. So indeed, we have shown that the prediction of the fatigue response starting from the process parameter is not possible with other methodology, and in particular, it would not have been possible to explore the literature data, and it can be also integrated into existing approach. So it can be useful and support the design, okay? And make this design process more efficient. Then we have seen that AI can be also used for surrogate models. So we can use multi-scale approach, which are very effective, but may involve high computational time. AI can predict the relevant properties in a negligible time by training the algorithms on synthetic data. But the simulated data, I would like to remark, these should be validated experimentally, and this can be used also for metamaterial design, but I have no time to show some application, okay? So, in my opinion, the answer is yes. AI can support the design and structural integrity assessment and parts. It allows for more efficient and effective design process, which is beyond what is achievable with traditional methodology. And it is up to the researcher to identify the areas where AI we have to select the proper area. Otherwise, it can be useless, okay? This is a conclusion important. We need also, this is another conclusion, trustworthy data to obtain reliable and accurate results. Okay, if we don't have good data, we cannot take good prediction. And before concluding, I have another question. Is AI mature enough to play an industrial role or to be effectively used in industrial practice? We have an increasing number of papers we have seen before. We have many lines of codes, okay? For example, some Python script. But in my opinion, it's not, okay? Because we have to translate and shift our research into something which can be easily used. And no one would like to write Python code to design additive manufacturing parts. I don't want to do it, okay? I think that you don't want doing it, okay? So, which is the solution? For example, integrating our codes into AI agents, okay? This is an example of the AI agent based on a definite neural network, which I have developed very recently. Here you can enter the process parameter to obtain, you can prompt the process parameter to obtain the probabilistic defect size without any programming strategies. So we have this is not so beautiful, but it can be changed, the interface, and become more readable, okay? And here you can find the results just in one click, okay? So in this case, if we have a tool like this, also for industrial application, we can exploit and boost the diffusion of the algorithms that we have developed, okay? But this is in progress, and this is an activity very, very recent, okay? So this is the research group I belong to. You can see some pictures, beautiful picture, but this depends on the point of view. Okay, here you can find some of our paper in which you can find details on our implementation. Since in this presentation, I have not focused on the implementation, okay, but you can find details here. And these are my contacts if you want to ask for other information, to collaborate. And thank you for your attention.